Section 1.8 is page 96, talks about proof methods and strategies. Here we're going to talk about a few different types of proofs that we're going to work with and see examples on. The first one is called exhaustive proof. Some theorems can be proven by examining a relatively small number of examples. Such proofs are called exhaustive proofs or proofs by exhaustion, because these proofs proceed by exhausting all possibilities. An exhausting proof is a special type of proof by cases, where each case involves checking a single example. So, there we go. Now, sometimes you cannot prove a theorem using a single argument that holds for all possible cases. So we introduce a new method that can be used to prove the theorem by considering different cases separately. This method is based on a rule of inference that we will now introduce. So to prove that this P1, statement P1, or P2, or P3, all the way to Pn, implies Q is tautology, that means you really want to prove P1 implies Q and P2 implies Q, and so that's what these are. This can be used as a rule of inference. This shows that the original conditional statement with a hypothesis made up of a disjunct of the propositions P1 through Pn can be proven by proving each of these conditional statements individually. So, looking at page 113, problem number 2, it says use proof by case, which is exhaustive proof, to show that 10 is not the square of a positive number, and they give you a hint. Let x be a positive integer. Well, case 1. Let x be between 1 and 3. Then x squared is less than or equal to 9. So x squared cannot equal 10, since it's less than that. Well, what if I chose x to be bigger than or equal to 4? Then x squared is bigger than or equal to 16. So again, x squared cannot be a 10. Oh, that's not a 0. That should be a 10. My mistake. Right? Well, between the two cases, we represented all values of x, and in neither case x squared was 10. Therefore, x is not the square of an integer, and that's because we exhausted all possible integers, and that didn't work. Another case, so a proof by cases must cover all possible cases that arise in the theorem, and here's one. This one is a bit lengthy, but I'm going to shorten it a bit. Prove that there are no positive perfect cubes less than 1,000 that are the sum of cubes of two positive integers. So let's look at the cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 125, 216, 343, 512, and 729. So prove that there are no positive perfect cubes less than 1,000 that are the sum of cubes. Well, let's see. These are the cubes. If I take 1 plus 1, so here I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 choose 2. And then I have the number with itself, so that's plus 9. Meaning 9 choose 2, that means you choose distinct. 1 and 8, 1 and 27, 1 and 64, 1 and 125, 1 and 215. But to use 1 and 1, 8 and 8, because it says prove that for any, proves that there are no positive perfect cubes less than 1,000 that are the sum of the cubes of two positive integers. Well, if I take 1 plus 1, that's 2. If I take 1 plus 8, that is 9. If I take 1 plus 27, that is 28. None of these are perfect cubes. 1 plus 64, that's 65. This goes on. I'll run out and I'll use, okay, how about 8 plus 27, that's 35. 8 plus 64, that is 72. And 8 plus 125, you list them all up. Then you go for the third. Oh, I forgot the 8 plus 8. Now I'm going to go for 27 plus 64. 91. So again, that's not a perfect cube. 27 plus 125, and the list goes on. Now altogether, I'm looking at 36 plus 9. There are 45 of those. So if I exhaust all of them, I'll be certain that these are cubes, but the sum of those will not be cubed. In general, when the phrase without loss of generality is used in a proof, often abbreviated for without loss of generality, we assert that by proving one case of the theorem, no additional argument is required to prove in other cases. Alright, so let's look at example 8. It says, prove using the notion of without loss of generality that 5x plus 5y is an odd integer, where x is an integer and y is an integer of opposite parity. That means one of them is odd, one of them is even. So let x and y be integers of opposite parity. If you know what parity is, one even, one odd. So in this case, I could say without loss of generality, without loss of generality, let x be the even and y be the odd. Again, you could switch them, but it's not going to matter. That means x equals some 2a and y equals some 2b plus 1, where a and b are integers. So if I take now what they have, they say without loss generality, using that this is an odd integer if x and y have opposite parity. Well, let's see. 5x plus 5y. X would be 2a and y would be 2b plus 1. So altogether, I'm looking at 10a plus 10b, not 10b. Yeah, 10b plus 5. Which equals 10a plus 10b plus 4 plus 1. I could factor a 2 out of that. That's 5a plus 5b plus 2 plus 1. Well, by definition, this is an integer times 2 plus 1. And that is pretty much what the definition of odd is. which satisfies the definition. Satisfy the definition of being odd. So that's sufficient. Anytime you want to show odd, just show 2 times an integer plus 1. Okay, let's fix the other one. Okay. Many theorems are assertions that objects of a particular type exist. A theorem of this type is a proposition of the form there exists a p of x where p is the predictor. There's just an x times p of x such that p of x is the predictor. A proof of a proposition of the form there exists an x and p of x is called an existence proof. There are several ways to prove a theorem of this type. Sometimes the existence of a proof there exists a p of an x can be given by finding an element A called a witness. Such P of A is true. This type of existence proof is called constructive. It is also possible to give an example, to give an existence proof of a non-constructive. That is, we do not find all the elements A such that P of A is true, but rather we prove that there exists an element that is true for some other way. So let's look at that and figure out how this works. Problem number 10. It says, prove that there is a positive integer that equals the sum of a positive integer not exceeding it. Is your proof constructive or non-constructive? So 1 has this property. Right? So prove that there is a positive integer that equals the sum of the positive integers not exceeding it. Well, 1 has that. Since 1 is the first positive integer, right? It is the only positive integer not exceeding 1, so the sum of that will be 1. And therefore the sum is 1. This is pretty much constructive proof. How about the next problem, or the next example? The next one's talking about prove that either this or this. Prove that either this or this is not a perfect square. So they give us a number, they say, is your proof constructive or not constructive? Prove that 2 times 10 to the 500 plus 15, 2 times 10 to the 500 plus 16. So this makes those consecutive. Those are consecutive integers. It's not working. Let's do it right. Here we go. Those are consecutive integers. And from what we know, the only perfect squares that differ by 1. So the only consecutive integers that are perfect squares are 0 squared and 1 squared. Any other square cannot differ by 1. The next one is 4. The next one is, so you know, this is 0 and 1. Those are consecutive. Anything other than 0 and 1 will not be consecutive. Therefore, this is a non-constructive proof. And that's pretty much it. You say those are consecutive. Besides 0 and 1, there are no other consecutive perfect squares, right? So therefore, the two consecutive integers could not be perfect squares. So that means either this or this is not a square. If one of them is, the other one isn't, because they're consecutive integers and they're not 0 or 1. Let's move that bottom one up. There we go. All right. Now we get to 14. 14 is stating, show that the product of two numbers this is another number. The idea, of course, is not to plug this in a calculator. And the third number so it says, show that the product of any two numbers is non-negative. The product of any of these numbers is non-negative. Well, let's see. We have three numbers. So we have at least two of them. That's 1, 2, 3. So we know that at least two of them must have the same sign. So at least two of them must have the same sign, meaning either they're all positive, that means two of them have the same sign, they're all negative, two of them have the same sign, or you could have a positive and a negative, but then the one after that is going to be either this or that, which means at least two of them have the same sign. And the product of two numbers with the same sign is positive, right? And if one of them is 0, well, that wouldn't be negative. That's non-negative still. So when they say show that the product of two of these numbers, those two numbers, if they're all positive, multiply two of them, you will get a non-negative. If they're all negative, multiply two of them, two negatives will give you a non-negative. If one is positive and one is negative, the last one must be either positive or negative. If it's positive, choose those two. And if it's negative, choose those two. And that product right there will be non-negative. And this is, of course, this is non-constructive. And 16 is next. 16 reads, prove or disprove that if A and B are rational numbers, if A and B are rational numbers, then A to the B is also rational. All right, well, let's say A is 2 and B is 1/2. Then A to the B, this is rational and this is rational. But if you take A to the B, that is 2 to the 1/2, which is square root of 2, this is irrational. So this is a counterexample. Therefore, this statement is not true, it's false. Now let me fix this. Some theorems assert the existence of a unique element with a particular property. In other words, those theorems assert that there's exactly one element with this property. To prove a statement of this type, we need to show that an element with this property exists and no other property. No other element has the property. the same property that is. The two parts of a uniqueness proof are existence and uniqueness. We show that an element X is with the desired property, then we show that X and Y both have the same desired property. So showing that there is a unique element X such that P of X is the same as proving there exists an X such that P of X, or there exists a Y. If Y doesn't equal X, that doesn't imply P of Y. Well, let's look at number 18 and see how this works. It says, show that if A, B, and C are real numbers, let A, B, and C be real numbers, and let A not equal to 0. Then, there's a unique solution to ax squared x plus b equals c. There is a unique solution. Well, okay, of course there is here. Ax equals c minus b, and x will be c minus b over a. Since a cannot be 0, well, this is unique. This is one of a kind, right? There it is. Use forward reasoning to show that if x is a non-negative real number, let x be bigger than 0. Non-negative real number. X belongs to reals. Then you want to show x squared plus 1 over x squared is bigger than 2. It says start with the inequality. So start with x minus 1 over x squared. That has to be bigger than or equal to 0. Which holds for all non-zero. Okay, we just take it and follow. So if I FOIL this, isn't that x squared minus twice the product of those plus the last squared? That is x squared minus 2 plus 1 over x squared is bigger than or equal to 0. Move the 2 over. Isn't that x squared plus 1 over x squared being bigger than or equal to 2? And therefore, we have just proved that property that they want. Now, how do you think of using the hint that they gave us? If I give you a problem like that on your test, I will give you the hint. This one, also they give us a hint, and without the hint, it's pretty much not possible to do this proof, but let's see. Well, it's not, let's say it's possible, it can be hard. Prove that there are infinitely many solutions in positive integers x, y, and z the equation x squared plus y squared equals z squared. So here they're saying prove that there are infinitely many solutions in positive integers x, y, and z to this equation. Well, they give us a hint. They say, why don't you let x equal m squared minus n squared, and let y equal 2mn, and let z equal m squared plus n squared, where m and n are integers. We could say this too. That's a notation for integers. Okay, well, let's see the hint. If I take, so I want to prove the blue. If I take x squared plus y squared, isn't that m squared minus n squared plus 2mn squared? Isn't that m to the fourth minus twice ab plus b squared plus 4m squared n squared? Wouldn't these two subtract and get me m to the fourth plus 2m squared n squared plus n to the fourth? Isn't that m squared plus n squared. And by definition, isn't that z squared? Since m and n are arbitrary, oh boy, since m and n are arbitrary, we have infinitely many solutions. And why is that? Well, there they are. That's what m and n are. They could be any of those. So the possibilities of m and n are limitless. Oh, that's very good. It's right there. All right. How about this problem? It says, prove that between every rational number, let a be rational, and every irrational number, let, or x, we'll be using x, let x be a rational number. So prove that between those rational and irrational, there is an irrational number. Well, let's see how we're going to do this. If I look at the average of two different numbers is always between them. So if I take the average to be a plus x divided by 2, and if I cross multiply, and wouldn't that mean that x will equal twice a minus a? Well, let's think about this really quick. Since x is irrational, this has to be irrational. But I know that a is rational. So it must be that 2a is irrational. And if 2a is irrational, then a is irrational as well. Now, we have a gorgeous theorem in the book called Fermat's theorem. I strongly suggest you read about it. And that theorem is on page 111. Make sure you read the history of it too. It says, you know, you have x squared plus y squared equal z squared or c squared. It says, if you make it an n, the equation, this equation, has no solution in integers x, y, and z, with x times y times z not equal to 0, whenever n is an integer bigger than 2. So 3, 4, 5, 6, and so on and so forth. So on page 111, I strongly suggest you read that.